Cache problem set 3. Quick disclaimer, I'm not a TA, I don't have an answer key, and I have no guarantees on whether I have assumptions that are correct, and no guarantees on whether my answers are also correct. I'll be putting in all the timestamps for every subproblem and timestamps for skipping background information. Let's get started. So for problem 1a, we want to find out some numerical thing that caused the program to run slower from its run on the 32 kilobyte cache to its run on the 64 kilobyte cache. So the first thing we'll be looking at is this equation to calculate the CPI. That equation is CPI equals base CPI plus memory CPI. The base CPI is what we would have if we didn't have issues with memory, and the memory CPI accounts for the extra cycles per instruction that we get because sometimes we incur a memory penalty. Memory CPI is calculated with the memory accesses per instruction multiplied by the miss rate multiplied by the miss penalty. So here they've given us that the original CPI was 1.25, and they've actually given us everything else as well. So the only thing here that we don't know is the base CPI, and that's what we'll be solving for. For memory accesses per instruction, we can see that this benchmark workload or program has 20% loads and 5% stores. This means that we have a total of 25% instructions that are memory accesses. So this means that the memory accesses per instruction is 0.25. They've given us a miss rate of 0.08 or 8%, and we know that the miss penalty is 20 cycles. So after solving this out, we'll come out to base CPI equals 0.85. So this is going to stay constant for the rest of the problem. Now that we know the base CPI, we're going to calculate the CPI of the new 64 kilobyte cache. So again, we'll do CPI equals base CPI plus memory CPI. We know that the base CPI is 0.85. We also know that the memory accesses per instruction will not change because we're still running the same program. We're given that the miss rate has gone down to 4%, and I'm assuming that the miss penalty is still at 20 cycles. The only reason I'm assuming this is because it says here the L1 miss penalty is 20 cycles, and it doesn't say was, whereas here, when the CPI changed, it says was. On a test, I would strongly suggest you ask a TA or the instructor to make sure that that assumption is valid. So I did some calculations, and the CPI for the 64 kilobyte cache is 1.05. So the next part of the problem is to figure out what actually solved the slowdown. What actually caused the slowdown, since we see that the CPI itself has gone down between the two. The execution time formula, which is what we'll be looking at, is determined by the instruction count multiplied by the CPI multiplied by the cycle time. So we know that the execution time slowed down from the first cache to the second cache by 3.2%. So if we take a look at this formula, we know that the instruction count has stayed the same since the program that we're running is the same benchmark workload. We've calculated the two CPIs, and we know that this isn't the contributing factor. So the only thing that we have left is the cycle time, so we can assume that the cycle time increased with the second cache. So if the question had just asked us to figure out what was causing the slowdown, we'd be done here, and we can just say it's the cycle time, but since it asks for a quantitative deduction, we have to keep going to find the numerical ratio. So using the execution time formulas and the node numbers, we'll be finding a ratio between the old and the new cycle times. First, we're going to write all the equations that we can come up with. The execution time for the old cache is the instruction count times the old CPI times the old cycle time. The execution time for the new cache is the instruction count times the new CPI times the new cycle time. And we also know from the problem that there was a 3.2% slowdown in execution time, so we know that the execution time new equals 1.032 execution time old. So we have two unknowns, cycle time old and cycle time new, and we have three equations, so we'll be doing some substitution and basic algebra. First, I'll be substituting in what I know for execution time new, these two things. So instruction count times CPI new times cycle time new equals 1.032 execution time old. And here I'll be substituting what I know for this right here. So now we have instruction count times CPI new times cycle time new equals 1.032 instruction count times CPI old times cycle time old. We can cancel out the instruction count, and since I'm going for the ratio between the new and the old, I'm going to move this over here, and we'll end up with cycle time new over cycle time old is equal to 1.032 CPI old all over CPI new. And since we know the values for both of these CPIs, we're going to go plug those in. And if we solve that, it becomes 1.229. So therefore, the new cycle time is 22.9% slower, and this is quantitatively what led to the 3.2% execution time slowdown. Alright, so for problem 1b, we're looking for the performance impact on the given workload when we make this change to the cache. So in other words, we're looking for the change in execution time. So there are two ways to interpret this. We can either compare the new 64 kilobyte cache to the first 64 kilobyte cache with the 4% miss rate, or we can compare it to the original 32 kilobyte cache. So I chose to compare it to the original 32 kilobyte cache. So first, we're going to calculate the CPI with this new cache, and we're just going to be using the same CPI equation as before. So we know that the base CPI is going to stay the same since it's not affected by memory stalls. We know that the memory accesses per instruction is also the same because we're running the same program. We know that the miss rate has gone down to 2% or 0.02. And we also know that the miss penalty is 20 cycles. So we know this because Professor Van Kat said it was fine to assume this on Piazza. So this comes out to 0.95. So this is the new CPI. And we're going to compute the execution time ratios between the two caches that we're comparing. So again, we're going to write down every single equation that we know with the execution time. So execution time old equals the instruction count times the CPI old times the cycle time old. We know that the execution time new equals instruction count times CPI new times the cycle time new. And we know that from the equation that we found in 1a, cycle time new equals, and here I'm going to use the actual value instead of the rounded value that I found, so 1.2286 times the cycle time old. So again, we have two unknowns, execution time old and execution time new, and we have three equations. So first we're going to substitute in what we know for cycle time new right here. So execution time new equals instruction count times CPI new times 1.2286 cycle time old. And here I'm going to be using what we know from this equation. I'm just going to quickly, cycle time old equals execution time old all over instruction count times CPI old. So we're going to be putting that in here. So execution time new equals instruction count times CPI new times 1.2286 And then here we're doing execution time old. And this is all over the instruction count times the CPI old. We can see immediately again that the instruction counts will cancel out. And since we're trying to find the ratios, this will go over here. So in the execution time new over the execution time old is 1.2286 CPI new all over CPI old. So this is pretty similar to what we found in terms of like a format for the ratios of execution times as we did for the ratio of cycle times. Again, we know all the CPI, so we're just going to go ahead and plug those in. 1.2286 times 0.95 all over 1.25, since this is what since I'm comparing it to the old cache, and this comes out to 0.9337, and I'm just going to subtract this from 1 minus 0.9337 equals 0.0663, and this is just a 6.63% difference in the new and the old execution times. So that's the answer for problem 1b. Alright, for problem 1c, we're going to try and figure out what the answer to problem 1b would be if we had started out with a unified cache. So up until now, we've been working with a split data cache, so there are several ways to interpret this problem, and depending on how many steps you redo with the new unified cache. So I chose to do this problem starting from the very beginning, from the beginning of problem 1a. So first, I'm going to calculate the CPI of a 32 kilobyte cache if it were unified with an 8% miss rate and 20 cycle miss penalty. So CPI equals base CPI, memory CPI, and we know that the base CPI is going to stay 0.85, and this time the memory accesses per instruction is going to change. So we know that with a unified cache, we're storing both the data and the instructions. And so for every instruction we load, we're guaranteed to have to load or to go into the cache, since we're loading the instruction. So that's 100%. And then we're still going to be adding a 25% memory accesses in the program, because still 20% of our instructions are loads and 5% are stores. So this comes out to 1.25 memory accesses per instruction for this program. We know that the miss penalty, or the miss rate on this original cache, was 8%, and we know that the original miss penalty was 20. And this will end up coming out to 1.85. So then we're going to calculate the new CPI for the unified 64 kilobyte cache with a 2% miss rate. So again, the CPI equals the base CPI plus the memory CPI. We know that it's 0.85 for the base CPI no matter what. We know that it's still 1.25 since the program hasn't changed. And this time we're doing it with the 2% miss rate and 20 cycle miss penalty. And this will come out to 1.35. So the next thing that we need to do is that we need to calculate the difference in cycle time, just like we did in problem 1a. And I'm just going to take a little bit of a shortcut here. We know that from what we did in 1a, right here, that this was actually our formula. So we're just going to be plugging in everything that we know. We know that the CPI old is 1.85, and we know that the CPI new is 1.35, And this will come out to somewhere around 1.590. I did a little bit of rounding here. So now we have the cycle time ratio. We're going to solve for the execution time ratio, as we were supposed to do in problem 1b. So we're just going to use the problem, or the formula that we found in 1b again. But instead of using this 1.2286, I'm just going to use what we found for the cycle time ratio in problem 1c so far. So here, instead of 1.2286, it'll be 1.590. And since we know these two numbers, we're just going to plug them right in. So the ratio is 1.590 times 1.35, and that is all over 1.85. And this is going to be 0.753. And this is less than 1, so we know that there's a execution time speed up. Subtract this from 1, and you'll get 0.247. So we know that there is a 24.7% increase or decrease in the execution time between the unified cache and the split cache. So that's the answer for problem 1c. So for problem 2a, there's going to be a little bit of background explanation. So this question is asking us to find the read and the write bandwidths for this program. So it's relatively straightforward. So this background information is covered in Cache 2 slide set. So you might want to follow along with one particular slide. I'll put it up on the screen somewhere. So as explained in lecture, storing in memory is a little bit different from loading in memory, because loading or reading doesn't need to change the memory, but storing does. So if we're using a cache, we need to make sure that anything we change in the cache also changes in the memory, because we need to keep the cache and the memory consistent. The two ways that we can keep the two consistent have to do with when we update memory. The first method is called write through. So this is when we update the memory as we go. So whenever we write to the cache, we also write through to main memory. It's sort of like writing on carbon paper that creates multiple copies of a form, for example, as you write. So this is real time. The other method is called write back, and this is when we update the memory only when the line gets evicted from the cache and if it's marked as dirty, which means that the line has been modified during its time in the cache. So consider this analogy. When you're making a PDF from a Word document, any edits that you're making to the PDF, let's say you found like a mistake, you have to go back to the Word document and you have to make the edits there first before you're able to save it as a PDF file. So it's not real time, and the PDF isn't going to be creating and editing itself as you write in the Word doc. Hopefully that's not too confusing. The other thing that we need to take care of is how we make room in the cache when we have a store miss. So again, there are two ways to take care of this. The first method is called write allocate. This means that when there's a store miss, we'll go ahead and write the data into the cache. So this is like us allocating space in the cache for the data. And the other method is called write around. And in this case, we're basically just going around the cache and we're ignoring it in favor of just writing to memory. So if we look at this problem, we have a cache. So there are 4 different scenarios when we're dealing with memory accesses. So we have a load hit, a load miss, a store hit, and a store miss. So to solve this problem, we're going to need to figure out what happens in each of these scenarios. We know that it's a write through, write allocate data cache. So for a load hit, we don't actually need to do any reading or writing. For a load miss, however, we'll need to read the line from memory so that we can put it into the cache. Note that we're not actually double counting this, so we're just going to write down that for a load miss, we're going to be reading 64 bytes. And now for the next scenario, a store hit, we know that we're dealing with a write through cache. So we're going to be writing whatever we write to the cache to the memory. So we're going to be writing 8 bytes to the memory. For the final scenario, we have a store miss. So we know that we're dealing with a write allocate. And so for this, we're both reading 64 bytes from the memory into the cache, and we're writing 8 bytes from the cache into the memory. So the next step is to calculate the CPI when we're running this program. So here's the CPI equation again. CPI equals base CPI plus the memory CPI. And for a classic in-order scalar processor like we have in this problem, the base CPI is just going to be 1, and this is something that was confirmed on Piazza. So let's take a look at the memory CPI portion. We can see here that there are 20% loads and 5% stores, so again, we have 25% memory accesses per instruction. Just to make sure though, we can see that it's a data cache and not a unified cache. So again, 0.25 is our memory accesses per instruction. We'll multiply this by the given miss rate of 5%. And we'll multiply it again by the miss penalty, which is 20 cycles. And this CPI is going to come out to 1.25. All right. So now we're going to calculate the number of bytes read and written what percent of the time. So you'll see why we need to do this in just a second. So I came up with a sort of formula. I can't remember where I got this from, but it is bandwidth is equal to the number of bytes that you're either reading or writing in any particular scenario. So if you're calculating the read bandwidth, you'll be looking at number of read bytes. And if you're calculating the write bandwidth, you'll be looking at the write bytes. You'll take that and you'll multiply it by the percent of instructions that result in that number of bytes being read or written. And you're going to divide all of this by the CPI. So let's start with the read bandwidth. So if you look at this over here again, we can see that there are two scenarios that lead to 64 bytes being read: the load miss and the store miss. Since we know that these are both misses, we'll just calculate what percent of instructions in this program lead to a miss. So that's pretty simple. We're going to take the 25% of instructions that are memory accesses, and we know that 5% of those instructions are going to result in a miss. And this comes out to 1.25% of all instructions in this program leading to a miss, either a load miss or a store miss. We also can see that it's always a 64 bytes being read, and we know what the CPI is. So let's plug all this in. And for read bandwidth, we're getting 64 bytes times what we found up here, the 1.25%. And I'll just go ahead and change this to 0.0125. And we're going to divide this by the CPI that we found, which is 1.25. This will come out to 0.64 bytes per cycle. I cannot spell. So this is the read bandwidth. We're going to be doing something pretty similar for the write bandwidth. So here we can see that for writing, we have two different scenarios, a store hit and a store miss, that both result in 8 bytes being written. We can see that both of these scenarios are stores. So for the percent, we can just look right up here, and it tells us that 5% of all instructions are stores. We also know that it was 8 bytes written for both of these scenarios. So 8 times 0.05 all over the CPI of 1.25. This comes out to 0.32 bytes per cycle. And this is the write bandwidth. That's not very well written. And there's your answer. Problem 2b. So this question isn't too hard to understand once you understand how to do 2a, since you're doing the same thing that we did in 2a, but instead of a write-through cache, we have a write-back cache. So to reiterate from earlier, this means that instead of writing to memory anytime we want to write to cache, we'll only write to memory when we evict the line from cache and that line has been marked as dirty. So let's figure out the 4 scenarios again. For a store hit or a load hit, or basically any hit, we won't be doing anything. However, for a miss, a store hit, a store miss, or a load miss, we'll be reading 64 bytes from memory into cache. However, because this is a write back cache, we also know that we need to be writing from cache into memory whenever we have a dirty line that's been evicted from cache. So this is going to mean that 30% of misses are also going to result in some number of bytes being written. So in this case, we'll be writing 64 bytes rather than just 8 as we did in problem 2a, because when a line is marked as dirty, we have no information on what part of the line was changed, so we just have to write the whole 64 byte line into memory. So just like before, I'll be using the equation bandwidth equals number of bytes read or written times the percent of instructions that resulted in that number of bytes read or written. And we're going to divide that all over the CPI, which we calculated last time to be 1.25. So let's calculate the read bandwidth first. And we'll see that the number of bytes that we read is again 64. And we know that for this, again, any number of misses, all the misses will result in 64 bytes being read. We calculated last time that it was a total of 1.25%, or 0.0125 of all instructions resulting in a miss. Again, we're going to divide this by 1.25, and the read bandwidth is the same as before. It's going to be 0.64 bytes per cycle. So for the write bandwidth, we again have 64 bytes being written, but this time instead of just doing the 1.25% of misses, we needed to take 30% of those 1.25% of misses. So this is basically like saying 0.3 times 0.0125 all over 1.25. And this ends up coming out to 0.192 bytes per cycle. So you can actually see that the write bandwidth went down between the write through cache and the write back cache, and hopefully this makes sense as to why. So that's your answer for problem 2b. Problem 3a. So let's break this one down. Problem 3 in general is asking about cache attacks, and I'll go more into detail as we need to for problems 3b and 3c. But for now, we're just dealing with cache conflicts when we're dealing with arrays of some size. So for this problem, we're trying to figure out how many bytes we need the cache to be so that we can run the given code without running into any conflicts. So let's take a look at the code. And in this case, we're looking at an array A filled with 4,096 doubles, which are 8 bytes each. And we can see that at most, we're accessing an element in the array once every iteration of the 512 iterations in this for loop. We can also see that we're accessing every 8th element in the array from this snippet I times 8. So with all of this information, we'll figure out the cache size. So first, we know that we're going to be accessing every 8 bytes, or one double, every 64 bytes. Every 64 bytes represents 8 elements in the array. We also know that each cache line is 64 bytes. So we know that each iteration of the for loop needs to have one line in the cache. So each for loop iteration needs 64 bytes. So technically we can just stop here and say, 64 bytes times 512 is 32,768 bytes, or 32 kilobytes. On my answer though, I also gave the number of sets in the cache, since we know we have 512 lines and each set is 4 lines. We have a total of 128 sets. Problem 3b. We'll get to background information in just a second, but for this question, our end goal is to find 4 addresses in our eviction set that will cause certain lines to be evicted from the original array in the victim code. So first, we'll talk about a prime and probe attack. In this kind of attack, the attacker is targeting a cache that the victim is using, and in this case, the attacker and the victim are both using the same cache. The attacker is going to try and cause the victim process to keep getting conflict misses, and in order to do this, the attacker has to fill up the set that they're attacking with their own data, so that when the victim tries to do stuff with that set, it'll result in a miss. The attacker can figure out whether there was a conflict miss by timing the loop. We know that misses incur a penalty, and so the attacker basically looks for that miss penalty. If this doesn't make a lot of sense right now, hopefully it'll make more sense as we move through the problem. We're only really interested in the first part of the attack, which is to cause conflict misses. In order to figure out what addresses we need from the eviction set, we need to figure out the actual index or set bits that we're targeting. To get this, we'll find the address of the element in the array when I equals 500 as stated in the problem. So when I equals 500, we're not actually trying to get element 500. Instead, we'll be looking for element 500 times 8. We know that each element is 8 bytes. So the address of the element 4000 is 32,000 bytes after the base address of the array. The base address of the array is 0x10000000. And so if we add these two together, we'll get in hex 0x10007D00. In binary, this is going to give us 0000101 1101. So now we need to figure out how to divide this long string of numbers into the tag, index, and offset bits. So I'll be referring to this slide from spring 2018. First, to figure out the offset bits, we'll look at this equation. We know that our line size, which is the same thing as block size, is 64. We know that 64 is 2 to the 6, so we know that our offset bits should be 6. Index bits is also relatively simple. We found that in 3A there are 128 sets in the cache, so according to the formula we should have 7 index bits, since 2 to the 7 equals 128. So if you go ahead and divide this number up into the tag, index, and offset bits, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. And the rest of this is tag. So that is the address of the 4,000th element of array A. So now that we have the index bits, the only thing left to do is to create 4 addresses that span the smallest range between the smallest and the largest address, and these addresses have to share the same index bits. I'm also going to use the addresses that are closest to the beginning of the eviction set. First, I'll get the base address of the eviction set in binary. We know that the eviction set has a base address of 0x15000000. In binary, this is 0001 0101 00. I'm going to split this number again into tag, index, and offset bits. We already know what index bits we want, and we'll only end up changing the tag and offset bits. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So now that we have this base address, first for the tag bits, we basically want to keep the changes as small as possible. We'll end up only incrementing the tag bits by 1, and we're going to do this by adding 1 to the rightmost bit in the tag bits. We know that the index bits have to remain the same as this up here, 11101000. Finally, for the offset bits, the smallest address should have the highest offset, while the largest address should have the lowest offset, and this will help get the smallest range possible. This means that the middle two could be any offset since they don't really affect the range between the smallest and the largest addresses. So now that we have these 4 addresses, we'll convert them to hex. I ended up just using an online converter because I was too lazy to actually think through these conversions. And when I was doing my problem, I actually had these all as ones. The reason I had these all as ones is because I copied and pasted from this first address right here. So for these answers, for hex, you would get 0x15001D3F, 0x15003D3F, 0x15005D3F, and 0x15007D00. And those are the 4 addresses that you need to answer this problem. Problem 3C is probably the easiest question in this problem set once you understand what it's asking. So I'll explain the flush and reload attack in just a second. Our end goal for this question is to find 8 addresses, all of which will be some offset from the base address of the array. And what we'll be doing for this question is finding out what those offsets are. So I'm not really 100% clear on the flush and reload attack specifics, but I think I understand enough to get this question. First, an attacker will flush a line that they're interested in from the cache. This is the victim cache. and then they'll wait for the victim to get to code that depends on the secret key that the attacker is trying to get to. And then the attacker will reload the cache line that they flushed to see what's happened and whether the victim has put anything back into the cache. So for this question, we're going to be repeating the same thing 8 times. We're interested in the addresses of the elements when I equals 8, I equals 9, and so on up to when I equals 15. So just like in 3a, we know that when I equals 8, we're actually looking at element 8 times 8. So this means we're looking at element 64. But since each element is 8 bytes, we're now 512 bytes from the base address. In hex, this is 200. So if we add this to the base address of the array, we'll get 0x1000 200. And we'll repeat this again. 9 times 8 to get the element that we're accessing, times 8 for the number of bytes, and this comes out to 576. We're just going to repeat this for the rest of these. So alternatively, you could have just added 64 bytes to this first address when I equals 8, which is the same thing as adding the number 40 in hex to these addresses. As you can see, there's clearly a pattern. But these addresses, these 8 addresses, are all you need to answer this problem. So that was all of problem set 3, caches, and hopefully you found this helpful. If there's anything else that you'd like me to explain or do a walkthrough of, just feel free to let me know and I might do it. For now, I'm going to go ahead and rest my voice and rest my hand. Good luck on problem set 4.